So our next speaker is Ashok VASEASHTA. I'm sorry for the pronunciation. From the International Clearwater Institute in Virginia. Good afternoon from Europe. Good morning to United States.
Yes, good morning from United States. Good morning to all of you. And of course, I thank the chair session for introducing the talk and obviously organizer for the kind presentation, invitation to this, kind invitation to this presentation. So as you could see, the title of the talk is Hierarchical Integration of Additive Manufacturing Processes and Electrospinning for Rapid Prototyping. This is a relatively new direction for us to integrate two existing methods to prepare some very unique structures. And I'm sure most of the people, those who are attending the conference, know that electrospinning is an effective and versatile technique which is used to produce porous structure ranging from submicron to nanometer diameter, high performance polymers and blends. We have prepared several porous structures, their configuration, which have become now possible for application in tactile sensing, energy harvesting, filtration, biomedical application, and so forth. However, these structures lack metricity, conformity, and desired three-dimensional single multi-material constructs which are necessary to mimic the desired structure. A simple yet versatile strategy is through employing digital controlled fabrication of shape morphing by combining two promising technologies such as electrospinning, also called additive manufacturing. And I saw Professor LeBlanc also had introduced this technique that lots of people are using. Our purpose is to combine the flexibility of the electrospinning membranes and use 3D printing to hold these membranes in place. And this presentation is essentially a hierarchical integration of the configuration through elaborate shapes and patterns that are printed on mesostructure stimuli responsive electrospun membranes so that we can then perform multiple function. This also allows us adjustment of any interlayer internal stresses which are induced by swelling or shrinkage mismatch, thus guiding the morphing behavior of electrospun membranes to adopt change in environment. So with that, let me give you a very brief outline of the presentation today. Let's see, it's not progressing on my screen, although this screen is small. So let me also change here. I have two screens, so I'll just continue to change both of them at the same time. Okay, good. So as you could see, I'll take you through a spectrum of applications that are possible with the integration of electrospinning and 3D printing. As motivation for this study, which as I mentioned is relatively new for us, integration of these two processes. So I'll take you which are manufacturing as I pointed before. So using digital control fabrication, I want to talk about some of the structures which are currently in progress. And this will be followed by a brief introduction to biopolymers. And the reason for that is we are cognizant of the fact that polymers are being introduced into the environment. So we are also conducting research on biopolymers so that there is less introduction of polymeric material in the environment, obviously to keep environment free and clear of plastic. And if the time should permit, then I'm going to take you through some of the advanced technological innovation platforms which we are working on. If not, I'll straightway go to the conclusion and then wrap the presentation. So as you see that we live in a highly connected world, what you see on the screen is different platforms which we can control using our cell phone. You also see a cell phone map of the application, which can control our video cameras, which can control UAVs, light going through the windows to control the temperature of the room, garage, and so forth. So we have an ubiquitous presence of sensors around us. And what we want to do is to provide these sensors in configuration which are rigid. At the same time, they have flexibility as well. So to hold these fixtures in place, obviously we want to have integration of these two processes, as I have mentioned. So in the following slide, what I have shown is essentially using electrospinning. We have been working on pressure sensing membranes. That is how different combination of polymers and bio-based polymers can serve as pressure sensing membrane. In addition, we have incorporated PVDF, I'll explain this a little bit later, for energy harvesting application, so that we have sensors that are pretty much.
You'll see the second.
Oh, okay, I'm sorry. As mentioned, I have two screens, so.
We are still at the slide. Now it's changed to connected world.
Okay, this is the slide I was talking. Thank you for pointing it out. As mentioned, I'm looking at 3-4 different screens on my monitor. So the one which I'm looking and the one which you are seeing is actually extremely tiny. So I have to coordinate. My apologies. So I'll be cognizant of this. Thank you. So using electrospinning, as I mentioned, we have worked on different types of pressure sensing membranes, as how different combination of polymers and bio-based polymers can serve as a pressure sensing membrane. We have also worked with PVDF, which as mentioned, I'll explain a little bit later, for energy harvesting system, so that we have sensors which are sort of self-powered for different applications, as I'm going to show you in the following few slides. This slide also shows some epidermal electronic systems to measure vitals for human body. And I'm sure lots of people in audience probably have Fitbit, which also has pressure sensing membranes, which continues to monitor vitals. And of course, at least in US, now it's a requirement by the military personnel to wear such devices so that their commander remotely can monitor their fitness level at their duty station. So what the configuration which you see on your screens, some of that we have worked on and some we continue to work on. We had also different projects from Natick Soldier Center to provide these types of membranes. Okay, so this slide, as mentioned, I'm coordinating these two. So I'm sure some of you probably have seen KardioMobile touchpad, which monitors your EKG. It's simply a piezocapacitive device that monitors pulse and displays the heart electrical activity. It detects 6 of the most basic arrhythmia with access to advanced algorithm to analyze your EKG. So as you know, PVDF, as I mentioned before, is a piezoelectric material, and many sensors in different configurations are used. So by electrospinning, we can make PVDF based configuration, and then of course we can integrate that with 3D into structures which are rigid enough so that it can provide those platforms to us. And of course, this is because of the ubiquitous presence of sensors. There is a steady increase in market share which you see on the slide as well. So let's move on to the next slide. I have a little difficulty here in moving slides, so my apologies for it. And also continue to coordinate with my screen. So these are some of the applications which we are working on and continue to work on, going from military to transport to agriculture to health and medicine and military application, as I pointed before. Some of these sensors which we are working are actually installed in remote location so that through this network configuration, we can continue to monitor different applications such as in military, health, medicine, transport, infrastructure, and so forth. So I'm going to show you some of the application in the following slide after giving this overview of the work which we are conducting. So, okay. All right. This is the work which I'm conducting as a part of my work in Transylvania University of Brasov. By background, I'm material/electrical engineer / physicist, but I have a position in civil engineering. So we are trying to make different types of sensors for structural health monitoring, which is normally carried out, as you know, by non-destructive valuation. And the problem with the non-destructive valuation is that you could only detect those areas which are easily accessible. But using sensors, which I have shown before, we can embed them in a sensor network type of configuration. These are, again, as mentioned, BCD-based electrosonic guides, which we can embed into different locations. And then in a network configuration, we can monitor the structural health of different types of infrastructure. The cost of these sensors is significantly reduced as compared to sensors which are made by other technology. So that's one reason why planning entrants can provide these types of sensors, which are very inexpensive and, of course, are useful, as you see on this slide. Okay. Some of the work which we are working on is for biomedical application. Using electrospinning, we have produced different types of membranes for wound healing, also for nerve regeneration, statin placement, PCL scaffold for bone regeneration. But the main problem in all of these membranes are that they are, although they are flexible, but they are not rigid, especially for some of the application, such as for external application, we need flexible yet rigid membranes. So although we can make using electrospinning, so integration of 3D does provide us capability to provide to make these types of membrane for rigid application. Since these membranes are fabricated using electrospinning, as I mentioned, they lack mechanical strength, so we integrate that with a 3D scaffold to hold such membranes in place. And this I'm going to discuss a little bit later in the presentation. So, okay, and I think I pointed out, okay, as I pointed out that there are many more applications, but the previous example only provide some glimpse for the present investigation. An additional aspect is the conventional, as I mentioned, conventional sensors are rigid, somewhat bulky, and inflexible since they are fabricated using kinetic processing method. So you spinning source copy 3D, yet flexible structures. They are mechanically strong, several characteristics you see on the screen, which is not even biodegradable. All right. Pardon me for this small delay. As I mentioned, I have to coordinate two different screens on my computer. So as you know, electrospinning is a versatile technique most of you probably have in your laboratory. It's inexpensive, extremely efficient, and reproducible technique that can be used to produce one-dimensional fibrous materials or composite with a wide range of diameter from nanometers to millimeter, simply by applying an electrostatic field to a polymeric solution. So with the recent advances in nanotechnology, we can make different types of multifunctional materials, which are produced by combining nanomaterials and polymers in electrospun configuration. The method involves essentially, as you know, electrohydrodynamic process in which a polymeric drop is electrified and it forms a Taylor cone and then proceeds towards the substrate where we can collect by using different methods. So this slide simply shows different configuration which we have made, and I'll show you also in the following slide a couple of configurations which are very commonly used. So these are two out of several configurations which we have used. A classical electrospinning setup is shown on the left, which basically consists of a syringe pump, a spinret, a high voltage power supply, and a ground collector, which can be modified with the addition of different collectors and needle tips. The second method is essentially coaxial spinning, and there are different other configurations which are used, but these two are by far the most common techniques which are used. The materials which are produced are particularly suitable for use as an extended drug release system, especially with the coaxial fibers. And we have produced application in tissue engineering, biosensors, filtration, wound dressing, drug delivery, and so forth. So this is another application which we continue to explore as we progress into this project. So in the following slide, I show you a table which actually took quite some time to generate this table. It has been published. This table simply shows different loading compounds / metals which were added to the polymeric solution for different applications. Although this data took quite some time to generate, we used a method called Taguchi method, and I'm sure most of you, those who do lots of processing, use this. It's a optimization process, and of course, it reduces the number of iterations. So we use Taguchi method to optimize the processing. And then later, we used different nature-based compounds for biomedical application, as you will see in this slide. Right here. Okay. So, we have used different types of extracts for green synthesis, such as lantana camara, T nanoparticles, turmeric, garlic for biomedical application, because they have therapeutic characteristics. So we could use biocompatible, biodegradable polymers along with these nature extracts for different therapeutic applications. So this is a very large body of work which is conducted by several postdocs in Turkey as our collaborators. So we continue to work on these applications. But again, addition of 3D printing then would help us make different constructs which are rigid and of course can be used for different applications. So that being the thrust of this presentation. So in the following slide, what you see are some commercial setups which are produced. Of course, in some of them, I was delighted to notice that they have referenced our work for making this commercial product. Some of them are in China, some in UK. But as you could see, these are multiple vendors for commercial electrospinning units for large-scale production of micro nanofiber using coaxial, multi-axial spinning, multiple jet spinning, and melt electrospinning, solution electrospinning, and so forth. So lots of techniques are now currently used essentially in different configuration of electrospinning. So in the following slide, what you see is a 3D, very basic of a 3D printing uh, setup. Okay, 3D printing setup, which is commonly known also as additive technology or advanced manufacturing technology. So the process makes 3D uh, this process makes 3D solid object from a digital file, as all of you know. In an additive process, an object is created by laying down successive layers of material until the object is created. And each of this layer can be seen as thinly sliced horizontal cross-section of eventual object. So what we have done is a strategic integration of electrospinning and this process to make different configurations. Okay, so in the following slide, what you see is sorry. These are 4 out of many configurations which are used for 3D printing. So as I mentioned, the process of 3D printing is based on layer by layer production of 3D structure directly from computer-aided design, drawing, fuse deposition, stereolithography, digital light processing, and polyjet photopolymers are commonly used in 3D printing techniques. And as mentioned, there are a lot more techniques. These are the 4 basic techniques which are shown on the screen. The method of deposition of polymer by fusion is a widely preferred process due to its advantage of being inexpensive and ease of use with polymer composition containing both thermoplastic polymers and also solid particles which are formed. Stereolithography is a low-cost, short-cycle process and high-precision process to manufacture complex shape structure. When this method is applied in presence of light projector, it simultaneously exposes the entire layer to UV light, and this process is called digital light processing. Again, as I mentioned, that these are some of the 4 common processes which are currently used, but we can also deposit metal. We can also deposit biological molecules using 3D printing. So it obviously provides a lot more flexibility for different types of applications. So in the following slide is okay, I just wanted to see, right. In the following slide, no, you have a different slide on this here. Yes. This is a combined technology which is called 3D jet writing. Electrojetting and also called electrospinning writing. This method in principle is described as a modified electrospinning process which produces 3D structure with unprecedented precision and resolution, thereby offering customizable pore geometries and scalability down to several millimeters. The polymeric liquid droplets at the needle tip are deformed and are accelerated towards the collector electrode in the presence of high applied electric field in a conical fashion. So charged polymer fibers jet accelerate towards the ground electrode, resulting in a fine pattern filament compared to the extrusion-based principle. So this is a versatile technique for producing essentially electronic circuits as well. So we are using this also in conjunction with, as I mentioned, electrospinning for applications, for different applications. Okay, so these are some of the examples which are currently in literature, one coming from my alma mater, Virginia Tech, and the other coming from a university in Israel where we have collaboration. So using 3D printing, as I pointed in the previous slides, nanotechnology and regenerative engineering have emerged at the forefront of these two versatile and innovative technology to foster novel therapeutic techniques and strategies, uh, especially in the current environment. The development of nanostructured biomaterials for tissue engineering, relevance of nanostructured material in tissue regeneration, and current application in nanostructured scaffold using 3D printing for engineering various tissue brain together of different emerging technologies. And as I mentioned, what you see on the screen is a researcher showing a 3D printed heart using patients' cells. And of course, Virginia Tech makes different types of prosthetic arms. So these are two institutions in addition to other institutions, those who are also using a combination of these two technologies. Pardon me. Okay, this is the same table which I had shown before. And the reason for this is that we are using uh, nanomaterials, which I'm sure all of you know. Let's see. My apologies, I have a problem in advancing the slides from my screen. So that's the reason there's a small delay. Okay, so we also add nanomaterials in the polymers. And of course, all of you know that using nanomaterials, because of their dimensional compatibility to fundamental physical quantities, uh, this allows material by design. So we could actually make these nanomaterials for selected application. And also the fact, as you know, that because of the pardon me, because of the fact that the reduced size obviously gives us more surface area. So that means there is a lot more surface activation, and hence these are good sensors as well. So by using nanomaterial, not only we can make good sensors, but also we can functionalize them with different types of capability. And by functionalization, we can make sensors for desired application. Additionally, because of this surface functionalization, we can attach functional groups to the surface, which is a way to transform a bioinert material to a biomimetic or bioactive material by coupling to different types of functional groups. So we use this also to make selective sensors. All right. As I pointed out, that we use different high performance plastic, and PVDF is one of them. As you see in this slide, the one of the semi-crystalline characteristic of PVDF is that it has good chemical and weather resistance and displays good resistance to distortion and creep at low and high temperature. Although the chemical resistance is good, the polymer can be attached by very polar solvents, primarily amines and concentrated acid. So PVDF has limited use as insulator because it's a dielectric, because of its dielectric properties. But the polymer is important because because of its relatively low cost compared to the other fluorinated polymers. And PVDF is unique because of the fact the material has piezoelectric properties. So that's the reason we try to use this as a energy harvesting device, as I'm going to show you in the following slides. So these are some of the characteristics of PVDF polymers, which are listed in this particular slide. As stated above, it's unique in that the piezopolymer has excellent piezoelectric properties. In 2001, of course, lots of researchers found that PVDF becomes super sensitive to pressure when impregnated with small quantities of carbon nanotubes. So by integration of nanomaterial and PVDF, you could make inherent superior mechanical and obviously energy harvesting application. So we use that as well, and it can be poured, and such polarization typically attributes to the redistribution of electronic or ionic charges within the solid or injected from electrode. And sometimes it's also, you could make it thermally reversible in PVDF, and polarization currents are produced by heating and or by cooling. So in the following slide, you will see some of the configuration which we are using for energy harvesting applications. I wish I had only one screen, which would be much easier to manipulate rather than combining two screens at the same time. So certain properties of PVDF are listed here, including structures of alpha and beta phases. As you know, the beta phase is the one which obviously produces the piezoelectric types of characteristics. It's a non-centrosymmetric phase, which is responsible for the piezoelectric effect. And these are some of the setups which we have in the laboratory. And this laboratory is actually in Alabama. This is part of a NASA group. So what you see is essentially a FTIR and Raman spectra of these polymers, simply indicating the ferroelectric beta phase in unannealed membranes at around 845 nanometers. So using this setup, we can compress, we can elongate, we could apply XR, which simply shows by applying pressure, we get change in capacitance. And this is the effect we are using to make different types of sensors. So we have studied stress versus strain along 3 Cartesian coordinates to help determine the method of operation, direction of electric field corresponding to the applied mechanical strain. So as mentioned, we have conducted different experimentation. So I'm going to show you a couple more slides. Of course, the time is limited because I want to get into the other applications as well. And okay. Yeah. So what I have shown out here is temperature versus the epsilon primary, and obviously the loss constant as a function of temperature. So these parameters can increase with the increase in temperature. However, we observe that a decrease in such parameters that's related to the porosity, and the observed decrease in dielectric loss with increase in temperature appears to be advantageous in conduction for us. And as mentioned, that lots of characteristics we have seen, and of course, lot still need to be characterized. These are some initial experiments which I have shown. We also conducted, let me see, the frequency dependence. So at low frequencies, free dipole in PVDF chain follow the orientation of the electric field at the same pace. At higher frequencies, dipole reorientation is out of phase with respect to lost my train of thought. The result is decrease in PVDF dielectric constant with increasing frequency. The high value of the dielectric constant at low frequencies may be influenced by Maxwell Wagner-Siller interfacial effect. The decrease in the interfacial polarization at high frequencies lower the imaginary part of the dielectric constant, and this can also be observed with dielectric loss, which is seen as temperature dependent. So as I mentioned, we have conducted different types of electrical characteristics of these polymers just to study how well they can be used in sensor and also for energy harvesting application. So in the following slides, I'm going to show you some of the applications. And this application, what you see on the screen, is for the structural health monitoring. As I mentioned, we can make different configuration by integration of PVDF membrane along with 3D constructs, which we can embed into different configuration. And that provides us, if there is any movement which is beyond the specification, which is allowed by a structure. And of course, we can integrate that in a network configuration so that we can remotely monitor all types of movement. So this is one of the current object which we are conducting with University in Brasov, and of course using integration of data analytics along with the artificial intelligence. It helps keep structures safe within the operating range. These are some of the biomedical applications which we are looking at. As mentioned, that it has tremendous application for biomedical application. And one of the interesting application is using DNA as a nucleating agent. PVDF has resulted in self-poured PVDF with high piezoelectricity. So we're using PVDF trifluoroethylene, which essentially causes crystallization directly into the polar beta phase, which is an excellent material for tactile sensing. So we're using as that embedded with the PVDF polymers. Such highly sensitive membranes have been experimented with different types of biomedical application, such as the reinforcement of tissue, self-guidance, cell guidance, vascular graft, ligament, and artificial corona. And I'm going to show you a couple of applications after I show the integration of the electrospinning and 3D printing as is seen in this slide. Okay. So this slide simply shows.
You have 5 more minutes.
Okay, I should be able to wrap up in 5 minutes. So as mentioned, I'm coming pretty close to the end of the presentation. As the small delay, as I mentioned, is because of the coordination of these two screens, so my apologies for that. So the production of nanofibers directly on 3D printed microfiber collector, as you could see, that we can continue to scan from one to the other and then make these types of structure. The software was pre-programmed to pause at specific layer to allow electrospinning before further printing can be resumed. So this is obviously the method which I have shown here has tremendous amount of applications. Okay, these are some additional application in era of COVID-19, where we can make different types of masks as personal protective equipment. Here is another application where we are making 3D scaffold by integration of melt electrospinning writing and conventional electrospinning techniques to make, again, different 3D networks with high porosity and high surface area, 3D controllable structure using, again, the structures which I have stated in the previous slides. Let's see. As I pointed out, that we also have application for 3D printed human physical augmentation by prosthetic arms, legs, ligaments, and so forth. So we can also prepare these types of stimuli responsive limbs. So this sort of gives us a overview of some of the applications we are looking into. But as mentioned, that individually we can prepare these devices for biomedical application and also using 3D. But integration of these two obviously is what I have emphasized in this presentation. So what you see is essentially application going from filtration to drug delivery to enzyme immobilization, energy generation, protective clothing, and so forth. So obviously it has tremendous amount of application. One of the results which we presented just a couple of months ago is what you see on the screen, that PVDF based membranes, we have put that on the finger. And of course, people, those who have Parkinson types of symptoms, they can be monitored at earlier stage. So this is what we had presented. Of course, it has a lot more biomedical applications which can be generated. And as a function of time, I'm sure also as additional collaboration, we'll continue to make these configurations. So, these are some of the applications which we were approached by US Army to see if we can prepare wearable kidneys, water desalination, water purification, breathable, protective clothing, and so forth. So these are all applications using electrospinning, which we already prepare, but to make them more flexible and rigid, integration of 3D printing would be very useful. So we are continuing to work on this as well. Very quickly, I want to point out that we have prepared the nanophotonic aspect of nanomaterials. And what this essentially does is, very briefly, it triggers optical clocking. And this has tremendous amount of application for multiple application, especially for military. So we are looking into that as well. And integration of these two technology would be very useful. So I'm going to actually pass this slide because this probably will take a little bit more time for me to explain. But I also wanted to point out very quickly that we are looking into different biopolymers, bioplastics, so that we could replace fossil-based polymers to biomaterials. Obviously, being cognizant of the fact that addition of more polymers into plastic would be harmful. So we are being cognizant of that. We are working on bio-based plastics and biopolymers for as greener alternative to different polymers which we used for 3D printing as well as for electrospinning. So this market is growing tremendously, knowing the fact, obviously, people, those who are working on plastic recognize that. So this slide simply shows as a function of time that this market continues to grow. So obviously the trend which I've shown is consistent with the trend globally. So here is, I believe, the conclusion. Okay, so the conclusion is the integration of electrospinning and 3D printing is a relatively new and upcoming field with unlimited potential. Of course, as I mentioned, that this is a fairly new method for us. So I limited example. It's a simple and straightforward method to successfully combine nanofibers to make the scaffold to make functional material for a variety of applications for rapid prototyping. So we have made proof of concept type of visualization. Different configuration for tissue engineering are possible, and also for variable textile. The spectrum of application is very large. Different specialized parts can be prepared by developing innovative solution, especially to COVID-19, for making personal protective equipment, human health. It has lots of application for human health, structural health monitoring. It has tremendous application in health monitoring also. And also, as I mentioned, that using bio-based plastics, and also polymers. I'm not a polymer scientist, but by coordinating or by cooperating with people, those who do are polymer scientists, we could perhaps make polymers by upcycling, meaning thereby that we could predict their characteristics as a function of time so that it reduces the need to reuse or recycle as a function of time. So we are integrating that aspect as well into into our fabrication processes. So with that, let me go ahead and conclude for today. These are some of the scientists, those who are coordinating with me. There are a lot more students, a lot more postdocs at 4 different locations, those who continue to help up in this project. And again, my apologies, because as mentioned, I was trying to coordinate actually 3 screens, believe it or not. One is larger and 2 screens in front of me. So it took sort of a little bit coordination to get 3 screens moving at the same time. And I thank the audience for their patience and listening. I'm open to any questions you may have for me.
Okay, thank you for your lecture. I was already checking here this chat session, and at the moment I don't see any questions. But well, in any case, we are behind our schedule. We will just move to the next speaker. Thank you. Thank you for the talk once again.
Absolutely. Thank you.
Okay, one information. We don't know whether we have another speaker according to our schedule.
Of course, she's here.
I suggest the next speaker will be ISyDMA’7.